All right, so the T distribution and degrees of freedom. So there are few cases where population standard deviation is actually known, right? We've been talking about being able to calculate the standard error, and we do that by dividing the standard deviation of the population by the square root of our sample size. But again, population standard deviation is very unlikely to be known, and therefore it is very unlikely that we can truly calculate the standard error of the mean. I'm not trying to be, coy in the fact that we just learned about this thing and now I'm kind of telling you we can't actually calculate it. Um, the importance is understanding how it is that we are able to make the generalizations that we can. Okay, it's a very important understanding of how this all of this math kind of comes together, so to speak. So, because we can't necessarily calculate the standard error of the mean, we need something to be able to obtain an estimate of the standard error of the mean. Sample variance and sample standard deviation tend to be smaller in comparison to population data, so we must account for these biased estimates. Which is all to say that we can determine the standard deviation and variance for a sample. But in order for us to be able to make the claim that the sample data that we're pulling is a good estimate of the population, we have to account for biases and the bias of having a smaller sample that is not the same as the population size. So the unbiased estimate of the standard error of the mean and T ratio. So please know, I am introducing you to these things, but these formulas are not formulas that I'm going to ask you to be putting into practice. Again, the importance of this is understanding what's happening on a foundational level of, thinking about statistics, so to speak. But I'm not going to ask you to use these formulas for anything. But you should know what they are. Make sure they're included in your notes. This is especially true for those of you who are moving on to, maybe taking Psych 124, if you're a psych major, or those of you who are interested in pursuing sociology or human development. This is important information, all right, for anybody, right, but especially those of you. So while we've learned the notation for populations, recall that we're primarily focused on collecting sample data. Therefore, instead of a sigma x bar, which is representative of the standard error of the mean for a population, we're now incorporating the lowercase s and the x bar. And so this represents an unbiased estimate of the standard error of the mean for samples. And so in this case, we're taking the sample standard deviation and we're dividing it by n minus 1. And as a reminder, n minus 1 is how we are accounting for the smaller sample size. We also learned that we can calculate a z-score for each sample using the z-score formula. However, we're now using estimated standard errors because we don't necessarily know the population standard deviation, meaning that our distribution of sample means has more variability. All right, they're more spread out. So this provides us with what's called the T ratio instead of a z-score. The T ratio formula is the mean, sample mean minus population mean, now divided by the unbiased estimate of the standard error of the mean. And then degrees of freedom. So the degrees of freedom are considered a statistical compensation for the failure of the distribution of sample means to assume the shape of a normal curve. Remember, I mentioned the idea with the central limit theorem that the more samples you take, the closer you get to infinity, the more that your normal distribution, the more that your distribution approximates a normal curve. Okay, but that's a theorem, right? The idea is that we don't necessarily see it in practice because the reality is we cannot take an infinite number of samples. So the degrees of freedom allows us to say, all right, well, we can't take an infinite number of samples, so, we have to make some sort of adjustment to how we're thinking about our samples so that we can safely use them in statistical analyses. So since we're working with sample distribution, degrees of freedoms allows us to account for assuming a normal distribution is occurring. The degrees of freedom, which is going to be the notation df, indicates how close the t distribution comes to approximating a normal curve. So for the t distribution, our degrees of freedom is n minus 1. This probably looks a little bit familiar in that we were using this to kind of account for the fact that we're working with samples and not populations. And so this becomes a foundation for how we are working through the statistical analyses that we're ultimately going to be using. To find the t value, so since we're working with t and not z, we'll actually be shifting over to what's called table C. The unit normal table is calibrated for all proportions under the normal curve, but again, remember, we can't necessarily have an infinite number of samples, so we don't know for certain that our sampling distribution of means necessarily approximates a normal curve. So instead of the unit normal table, we're going to use what's called table C, which is calibrated for various levels of alpha. All right, so this A here represents alpha. The alpha value represents the area in the tails of the t distribution. When I describe the tails of a distribution, we're saying, that's a rough one. If our mean is in the middle, the area, if we have these two points on our distribution that are delineating between what's called the body. The body is thought of as this bigger area, typically in between two tails. Then this down here is the tail, as well as this area over here. So when I say tail of a distribution, that's what I'm referring to. So the alpha value represents the area in the t distribution. And so in order to determine what the area is in those tails, we're going to calculate alpha. In order to do that, we're going to we are going to take 1 and subtract from that our level of confidence. I think I have the examples here. Remember, we're working with 95 and 99% confidence. So for a 95% level of confidence, our alpha value is 0.05. And the way that we do this, I'm actually going to work within this magnifying glass. If calculating alpha is equal to 1 minus the level of confidence, we can't subtract a percent, right? We can't say 1 minus 95%. What we can say is, let's convert this 95% into a decimal. 1 minus 0.95 will leave us with an alpha level of 0.05. Similarly, we cannot subtract 99% from 1, but we can subtract 1 minus 0.99, which equals 0.01. And again, this is our alpha level, okay? So just like the z-scores remain constant with 95% and 99% confidence intervals, so do the alpha levels, all right? So for 95% confidence, the alpha level is always 0.05. For 99% confidence, the alpha level is always 0.01. Then we're going to navigate table C. So we're not going to do it so much in the samples and populations piece of our modules. We'll actually see it more in the next module when we get into hypothesis testing and then t-test. However, in order to navigate table C, you're going to need 2 pieces of information: the degrees of freedom and the alpha value. As an example, if we wanted to construct a 95% confidence interval with a sample size of 20, in order to calculate degrees of freedom, we would take the formula n-1, plug in our sample size of 20, and determine that the degrees of freedom for this particular sample is 19. Since we want to work with a 95% confidence interval, and based on our understanding of the relationship between the confidence interval and the alpha level, we can automatically jump to saying that the alpha level is 0.05. If you're asked to find the t for a degrees of freedom that is not found on the table, I'll explain this more when we get into that later module. But if we're looking for degrees of freedom that we don't see represented, we'll actually default to the next smallest degrees of freedom. And then degrees of freedom over 40 fall so close together in t-value that it would be like splitting hairs. So we're not going to see degrees of freedom larger than 40 on table C. let's see. A slight adjustment must also be made to our confidence interval formula such that instead of using Z, now we're talking about T, right? Because the idea, again, is that we don't have the population information necessary to truly work with a Z score. We need that unbiased estimate, and we also need the T ratio. So we use T times the standard error, the unbiased estimate of the standard error of the mean. All right, so that's all I got. That's it for samples and populations. Hopefully, you're feeling okay, right? If you feel okay, that's a good place to be. I'm not expecting you to feel like an expert after all of this. If you have any questions, please don't hesitate to let me know.